promised, we're going to move from a Z-score to what is now called a Z-test. What is a Z-test, you might ask? We'll get there. So let's get into it. Here's our lovely overview as always. We're going to talk about all the Z's, Z-scores, Z-tests, Z-statistics. It's going to be great. We're going to look at how to calculate a Z-score again for one person. We'll play with the unit normal table again, address our 68, 95, 99 rule, and then we'll calculate some of our first Z-tests. It's going to be great. It's going to be great. We'll have one real-world example looking at Flint, Michigan water, some tips for the unit Z table, and a little bit of Z-scores and Z-tests in R. Without further ado, let's go. Oh, the Z's. Don't fall asleep. So here are all of our different Z's. The first one, the Z-score, we've already talked about. We did that in our last lesson where we translated one person's score into the standardized Z-scale, which tells us how many standard deviations above or below a person's score is from the mean. This time, we're going to start looking at Z-tests and the Z-statistic that comes out of that test. So a Z-test is a statistical test you calculate to determine a Z-statistic. The Z-statistic is basically a Z-score, but instead of being a score for just one person, it's a standardized score for an entire mean, a whole sample mean. But we can do the same things with it, like compare and look up probabilities. So let's go back to the probability for just one person's score, the regular Z-score, which we've already looked at. If the average height of women is 65 inches, about 5'5", and the standard deviation is 3.5 inches, what is the probability of observing one woman who is 68 inches or taller? So how likely is it that if you're just out walking about that you see some woman who is 5'8" or taller? So first thing we do, what's the first thing we do? We got to convert to our Z-score, which we do over here. Here is that 68 is the person's score that we are trying to figure out what's the probability of. 68, which is that 5'8" or taller. 65 was the average. Here's our standard deviation, and if you calculate that, boop, you get a Z-score of 0.86. Then what do we do with that? We go to that table, we look up that number, and we look for the proportion in the tail, because in this case we're looking for 68 inches or above. So if we go and do that, remember we're asking what is the probability of X, a person, a female, being greater, taller than 68 inches. And if we go and look up that probability on the unit table, we find that it is about 19% chance. So what is this curve doing here? Remember that the distribution is what tells us that probability. We have to go and look up Z. There's always going to be a Z down here. Remember, Z equals 0 is the mean. Here is our Z of 0.86, right here, this line. And we're asking how much proportion of this curve here, how much of that is related to this Z-statistic of 0.86. Remember, 0.86 is the Z-score for seeing somebody who is 68 inches or taller. Probability of that is about 19%. So observing one woman who is 68 inches or taller is pretty likely. You have about a 1 in 5 chance, a 20% chance. We know that there are tall women out there, so it's not super uncommon to see one that's about 5'8" or taller. Now let's look up between two values. So if the average height of a woman is 65 inches with standard deviation of 3.5, what is the probability of seeing one woman that is between 61.5 inches, which is about 5'1.5", and 68.5 inches, 5'8.5"? Before you all start any sort of problem, I want you to step back for a second and actually think about it just realistically. How likely do you think it is that you see a woman who is about 5'1.5" or 5'8.5", somewhere in between there? Remembering that most women are about 5'5". So do you think that would be super likely or super unlikely? Keep those kind of intuitions with you as you go through these problems. In this case, it's probably fairly likely. Most women are going to be around that height. So if you go and do a calculation and you get some really, really low probability, that would give you a clue that maybe you did something wrong. So again, what is this curve doing here? This is our probability curve, and this time we are looking for the proportion that is between two z-scores, but you could also write it as the two raw scores, the 5.1½ and the 5.8½. So let's go and convert the raw values into z-scores so we can look them up on the table. So here we're looking for the proportion between -1 and +1. Now there are a few different ways to get that answer using the unit table, but if you remember a particular rule, you would know right away that the answer is 68%, because between -1 and +1 standard deviations, about 68% of people fall in there. So there is a 68% chance that as you're walking out at the store, you'll see women between the heights of 5.1½ and 5.8½ So in case you ever have to look up something that's not as easy as -1 to +1, though I won't make you do it, you would have to go and look up on the unit table, and there are a few different ways to do this. You could determine the entire body, the proportion of the entire body, all the way up to, let's say, that +1 z-score, and then subtract that tail, the -1, from down below. And you can also use this table that has the last column here, tells you the proportion from the mean to that z-score, or the mean to the other z-score, and you just add the two. The unit table does not have negative values. You just look up the absolute value of the z-score, and depending on what the question is asking, you look at the tail or the body. Now, my helpful tip on how to know if you're looking for the tail or the body is forget this tail and body thing, and instead always draw the picture. The picture will let you know what you're looking for, and we'll see a few more examples of that. Going back to our example, as we've said, there is already a quick trick. If you notice that from -1 to +1 standard deviations, we know from our rules that what proportion falls between -1 and +1? 68%. So in this example, our quick trick immediately told us that from -1 to +1, 68% of women will have a height between 6.1½ and 5.8½. So going back to some of the rules of our curve, what z-values do 95% of the observations fall between? So we're looking for right here and right here. What are the corresponding z-scores? We have 2. We have -2 to +2. 95% of people will have z-scores that fall within -2 and 2 standard deviations from the mean. Now, as we continue with statistics, this 95% is going to become more and more important as we go along. But for now, it's time to go and look at our z-tests and z-statistics. We just calculate the z-score for one person, trying to figure out the probability of seeing one person that is a certain height, for example. But that's all well and good. Do we usually care about just one person's score? Not really, unfortunately. I mean, you are beautiful and great, and I very much care about your z-score, but, you know, if we want to make some bigger inferences about the population, we have to start dealing with a mean rather than just one value, one person's score. So now I want to know the probability of seeing an entire group of people, a whole sample mean that is of a certain height. Now we're going to run a z-test and calculate a z-score for a mean, but now that z-score is called a z-statistic. So let's dive in. Let's standardize. We're standardizing numbers. To calculate a z-statistic, it is very similar to the z-score. So here's our original equation with our z-score. We have our one person's value, or the one value of interest. We have the mean, and we have the standard deviation to give us our z-score. Now if we look at the z-statistic formula, it looks very similar, but now we're dealing with an x-bar, which means we're dealing with the mean calculated from a sample. We have our regular average. We have our standard deviation, which is now being divided by the square root of n. Let's investigate this equation just a little bit more. So this whole unit down here, the standard deviation divided by the square root of n, that value is called the standard error. And because we're dealing with the sample mean, we now have to take into account the number of people that were in that sample, which is why we incorporate that square root of n in there. So what's very important now to distinguish that instead of trying to calculate the probability of seeing one person, we want to know the probability of observing a whole mean of a certain value. So that's an entire group of people. So now, remember before we had this standard distribution where a person's score represented their z-score there, and we could figure out the proportion and the probability of seeing one of those people. Now we have a slightly different distribution. This one is called the sampling distribution, and now this is a distribution of means rather than people. So this value here is no longer just one person's score. This is a whole sample mean. Z-statistics tell us how many standard deviations away from the population mean one sample mean is. We're going to look at sampling distributions in more depth in the next few lessons. But for now, let's stick to getting familiar with calculating the z-test. So again, we have our sample mean minus the population mean divided by the standard error. And standard error is just the standard deviation, which we're already familiar with, divided by that square root of n. And this is the standard error. So now let's again step back and just think about things realistically. What is the probability of observing one woman who is 68 inches or taller? It's about 5'8". We now know that it's about a 19% chance. Pretty likely, right, to see one woman that's kind of tall. But now, if the average height of women is 65, standard deviation is 3.5, how likely is it that I collect a sample of 5 people and I calculate a mean of 68 inches or higher? Basically, I'm asking, what is the probability that I close my eyes and point at 5 women out in public and take their average, and their average height is 5'8" or taller? Which one do you think has a higher probability? The probability of seeing one woman that tall, and the probability of seeing a whole sample mean that is that tall? Do you think the probabilities will be different? How different do you think the probabilities will be? Again, before you start any of these sorts of problems, I want you to think about them just realistically, logically. How likely is it that you see a whole group of women that's 5'8" or taller? Now, 5'8" is kind of tall for a woman, but as we saw, it's not crazy rare to see one woman that tall. But how unlikely or likely do you think it is to see a group of 5 women who are 5'8" or taller on average? How different, again, do you think these probabilities will be? So if we standardize the value, then we can refer back to the z-table and see the probability of getting a certain mean just like we did for the one person's z-score. What do you think dividing by the square root of n is going to do to that z-value? Do you think it will increase or decrease the outcome, the z-statistic? By dividing by another number, is that going to make your z-statistic bigger or smaller? Think about that for just a second. These relationships are very important. By dividing by the square root of n, it's going to increase the absolute value of your z-statistic. It's going to push it further out into our distribution, into those smaller little tails. A higher z-statistic means a lower probability. And when I say higher, I do mean an absolute value. So it could be a really big negative number or a really big positive number. But the further out it goes on our curve, the lower the probability is going to get. So again, with our regular z-score versus our z-statistic, the z-value is going to be bigger for the z-statistic. Again, a higher z-value means the probability is lower. So the z-score will have a higher probability than any z-statistic, all other things being equal. As a z-statistic moves further away from that middle 0 point, the probability goes down. So the higher the z-statistic, the lower the probability. And as a z-statistic goes down, meaning closer to the middle, the probability goes up, because remember, that is where our hump is, and that's where most of the values live. So there is an inverse relationship between the Z-statistic and the probability that is associated with that value. I can't emphasize enough that this curve is all about probability. So again, let's say that we have a Z-score of -2, and it's probably about right here. And let's say that the probability of observing that is about 0.05, because look, if we go from 2 up and across to figure out what the corresponding Y value, the probability is, it's about 0.05. What's the probability of seeing a Z-score of 0? Remember, the Z-score of 0 is the mean, which is probably the most common value. So let's say in this example, the probability way up here is 0.5. That is what this curve is always telling us. So when you're looking for a Z value right here, you're going up that curve, finding the line, and going all the way across to figure out what that probability is. And as a Z value, an absolute value, gets further away, gets bigger, away from the mean, so if it goes into either of these two regions, the lower the probability is. The closer in it gets, the higher the probability. Because remember, this is the realm of averageness, that most people are going to be in here. So let's go and calculate our Z-statistic. What is the probability of observing a sample mean that is greater than 68 inches from a sample of 5 people? And this, by the way, is distribution notation. When you have this little, we have x, that's the variable of interest, which is height. We say it is distributed normally with a mean of 65 and a standard deviation of 3.5. You don't necessarily need to know that, but I think that's pretty nice shorthand. So let's calculate. So here we are. We take our 68. That is the value of interest. We want to know the probability of seeing a sample mean of women 68 inches or taller. We subtract the mean, 65, divided by, remember this whole thing is the standard error. Standard error is equal to the standard deviation divided by the square root of n. We do that calculation and we get 1.92. Now before we keep going, do you think that is a kind of high or kind of low Z value? Remember where it falls on the curve. We're kind of far out here probably. How high of a probability do you think that's going to be? First off, do you think it'll be greater than 50? Absolutely not, because it doesn't even take up half of the curve. So we know it's going to be less than 50, and that's very helpful when you're looking on the table. So here is our lovely table. Remember, there's a few different columns we can look at, and you might be confused and wondering which one do I look at. When you draw that picture, it really will help you figure out which the correct answer is, and when you actually take a moment to think about these questions realistically and not just statistically, that will help you to know which answer is correct. So remember, there's going to be a small probability of seeing a whole bunch of women with that high of an average. So we have 97%, a 3%, or 47%. This is the column that tells you from the middle to a certain value. So we definitely don't want this column. We know that the probability of seeing a whole group of women that are 68 inches or taller is going to be much lower than the probability of seeing one woman that is 68 inches or taller, and that probability was about 20. So it must be this one. This is the one that we're looking for, and it's about a 3% chance. So here I would also round to, for the probabilities, you can round the decimal to 2 decimal places. So here, our probability in this tiny little itty bitty tail here, the probability is about 3% chance. The chances of you seeing a whole group of women, 5 of them, that their average height is 68 inches or taller is about 3%. So this is a little bit more information about that distribution notation. A certain variable, in this case height, and we're saying it is distributed, that's what the tilde means here. Normally, that's what the n stands for, and it has a mean of and a standard deviation of. Again, you do not have to know this, but it's pretty neat notation, and if you do any other math, they might write out things like this. So now that we have both of these probabilities, let's really look at them and try to internalize these differences of observing one person versus a whole mean. So here was our example when we're looking for just the probability of one person, one female being 68 inches or taller, and we had a z-score of 0.86. And if we look for the probability and we went all the way across, we had a probability, all this over here is about 19%. Now, if we were to look over here at our one sample, we have a z-value of 1.92, and that is a much smaller little chunk. We only have 3%. So all other things being equal, a z-test will always have a higher value than a z-score. The probability of seeing one person who's really tall is a lot more probable than seeing 5 people that are really tall. So now let's look at an example with salaries. Let's say some large company has an average salary of $62,000 and a standard deviation of $32,000, which is quite large. If I select one employee at random, what is the probability that their salary is less than $59,000? So this one is just a simple z-score again. We're asking the probability of just one person. So we get 59,000 minus the mean, 62,000, divided by the standard deviation, 32,000. And we end up with a z-score of negative 0.09, which is pretty darn close to 0. So if we were to put that on our drawing, draw the picture, you'll see that if here's our mean, here's our z-score, we're looking for this huge chunk over here. Before we even go to the table, how big do you think that's going to be? If it's super duper close to 0, and we know that the proportion of 0 to the very end of either side is going to be 50, do you think that this value will be greater than 50, dramatically less than 50, or really close to 50? Probably really close, so let's see. Probability of a z-score less than negative 0.09. Now again, this is where I'm saying to draw the picture is really going to help you, because there is no negative on the z-table. You need to be able to kind of flip these things in your mind, which can get confusing. But if you draw the picture, that will always let you know. There's going to be the 3 columns, one that will be less than 50% and one that will be greater, and then that last column that we don't really use, that's all about from the mean to a certain value. In this case, do we want the value that is greater than 50% or less than 50%? Remember our drawing. It's almost at the mean, but it's a little bit less, and we're looking for that area to the left of it. So in this case, we want the value that is going to be a little bit less than 50%, and it ends up being 0.46. So there is a 46% chance that we see one person whose average salary is about $59,000 or less. Now let's do that same problem again, but this time I want to know what the probability of observing an average salary of $59,000 or less for a group of 100 people. What is that probability? So we're going to set it up just like our previous example. Like, all of this is the same. The only thing that we're adding new is dividing by the square root of 100. Remember, when we add in that square root of n part, that is going to increase our z-statistic, but it's going to decrease the probability. And in this case, we end up with a z-score of negative 0.94. We go and look that up on our z-table, and we will see that the probability is 17%. So notice before it was 40-something% versus 17%. Much higher probability of seeing one person versus a whole group of people with a mean value that low. Now I know at this point in the lesson you're probably thinking, why are we doing this? I know, I used to always wonder the same thing when I first started taking statistics. But this is going to lead us into more interesting things that we can do with statistical tests. In statistics, we don't really care about this straight yes or no. We normally want to know the probability of something, how likely or unlikely something is. We usually ask something like, assuming everything is similar to the average, what is the probability I see a sample that is really, really high or really, really low? Now, we've been dealing with this average height of women example because it's tangible and easy to think about. But let's move on to a slightly more real-world example of why statistics can be very helpful and powerful. Real-world example of Flint, Michigan water. So, is Flint, Michigan water contaminated? How do we test if Flint, Michigan's water is contaminated with lead? What do we need to ask, and what do we need to know? take a moment to think about this. What kind of questions do you need to ask, and what kind of information do you need to answer this question? So the things that we need to know to start are, what's the average amount of lead to expect in any water in America? Unfortunately, there are probably trace amounts in most water, but it's usually not cause for concern. So we need to know what that average value is. Now, some cities may have more or less lead in their water, but we need to know how much, on average, do the different cities differ from each other in their average amount of lead. And that is our standard deviation. How many Flint, Michigan water samples were taken? So we do have some answers to some of these questions. The first one is that the EPA says the average amount of lead in water is 2.8 parts per billion. Anything over 15 parts per billion is action level, which means that something has to be done. It's too high. So some cities have more or less lead than others, but what is the average amount of difference, the standard deviation? That's pretty hard to find, so I said for the sake of this example, it's 1.5 parts per billion. I would like to note that this is the only value that is made up by me for the sake of this example, but everything else is from actual studies and actual reports. So how many Flint, Michigan water samples were taken? In the particular report I found, there was 269. There was no overall average that they reported, but we do know that 40% of those samples, so about n equals 101, were over 5 parts per billion. The top 10%, so the 90th percentile of those samples, which was 27, was 25 parts per billion. And there were a few outliers that were over 100 parts per billion. One exceeded 1,000 parts per billion. Remember, the average is 2.8. 15 is the action level. So, is Flint, Michigan water poisoned with lead? Let's find out. Before we go and calculate a Z-test, let's actually see what's the probability of observing one water sample that's really, really high. So assuming that water is not contaminated, what is the probability you see one sample, not an average, with a lead concentration of 5 parts per billion or greater, considering the mean for the US is 2.8 with a known standard deviation of 1.5. So this is just a Z-score, like any other. We take 5 minus the average divided by the standard deviation, and we get a Z-score of 1.47. Because the question is asking 5 or greater, we are looking for this side. And if we go and look that up on the table, we see that a Z-score of 1.47 corresponds to a probability of about 7%. So assuming all the water is fine, there is still a 7% chance of seeing one water sample greater than 5 parts per billion. It's not impossible or completely unlikely to see some water samples with high levels of lead because samples vary. Maybe you sampled a particularly leady lead pipe, or maybe it was a really old building. But assuming all the water is fine, what is the probability of seeing, on average, from multiple water samples, 5 parts per billion or greater? Now let's go and calculate our Z-test. So assuming the water is not contaminated, what is the probability you see an average lead concentration of 5 parts per billion or greater from a sample of 101, considering the mean for the US is 2.8 with a known standard deviation of 1.5? So we're going to set it up exactly the same. Again, the only difference now is that we are also dividing by the square root of 101. Because this whole thing is our standard error, we end up with a Z-score of 14.74. Now I believe your Z tables stop at 4, and you can kind of guess that the probability is going to be incredibly low. It's probably more like out here somewhere, but I ran out of PowerPoint. So the probability of an entire mean being higher than 5 parts per billion with a sample of 101, when you know that the national average is 2.8, the possibility of that happening is really small. There's a number over here somewhere. It's 0.000000 something. There is a value there somewhere. But when we round, we end up with a 0% chance. So what does this tell us? Assuming that the water is fine, there is a 0.0000% chance of seeing an average lead concentration of 5 parts per billion from an average of 101 water samples. But there is still technically a really, really small chance. Somewhere after all those zeros, there's a number, and so it could just be a fluke. But what is more likely? That this was a fluke of 101 water samples, and that everything is fine, as some politicians may claim? Or is it more likely that Flint, Michigan water is contaminated and different from the 2.8 parts per billion average? What do you think? Now, this is the essence of hypothesis testing. This is why we need statistics. This is why we standardize values, so we can go and look them up and see what is their probability of happening, assuming everything is fine. This is the essence of that hypothesis testing that we're going to cover coming up. And now some z-table tips. When you calculate a z-score and when you look for a probability and you're going to report both of those, you can round to 2 decimal places. When you find the z-score that corresponds to a probability, which you can look up the probability and then go find the z-score. Go with the z-score that is smaller if you can't find the exact probability or the exact z-score. There are no negative z-scores on the table, but you can still look up negative values. For example, if the z-score was negative 1.5, you would look up 1.5, and based on the question, whether it's asking for greater than or less than, you pick either the body or the tail. Draw the picture helps. So next up, and for the rest of this course, we will focus mainly on means that we derive from samples, from one sample's mean rather than just one single observation, which is just one person's score. Next, we will shift our attentions to the process of taking a good sample. I will see you there. But not before we do some z-score, z-test, and probability in R really quick. So to do a z-statistic in R, you would tell R that this is the sample mean, this is the population mean, this is the standard deviation, and this is the sample size. Then you use this equation, just type this in line for line, and you will get a z-test value. You can then go and figure out the proportion. Instead of using the unit table, you can use these lovely functions in R, and they will tell you the proportion in that body or that tail. Now this example is from the Flint, Michigan water example. This part is the z-score, this part is the z-statistic, and the p-norm function below again gives you the probability associated with those z values. But I will see you in the next one.